Welcome to today's lecture on measure and integration. This is the second lecture, and in this lecture we are going to cover the following topics: algebra generated by a class, then we will look at algebra generated by a semi-algebra. We will also look at what is called the sigma algebra of subsets of X and sigma algebra generated by a class of subsets of a set X. Let us just recall what we called as the semi-algebra of subsets of a set X. It was the collection. So, let me just recall a semi-algebra C is a semi-algebra of subsets of a set X if had the following properties: empty set and the whole space belong to it, and secondly, for A and B belonging to C implies that the intersection of these two sets is also an element of C, that is, the class C is closed under intersections. And third property was that if A belongs to C, then this implies that A complement can be represented as a finite disjoint union of elements of the class C. That is, A complement is a union of elements C I, where each C I belongs to C and C I intersection C j is empty for I not equal to j. So, such a class was called a semi-algebra of subsets of X. Then we looked at what we called as the algebra of subsets of a set X. So, a class F of subsets of a set X is called an algebra if it had the following properties, namely empty set and the whole space belong to F, as in the case of semi-algebra. Secondly, A and B belonging to F imply that A intersection B also belongs to F, as was the case for the semi-algebra. And third property, which is different from the semi-algebra, which is a bit stronger than the semi-algebra, is whenever a set A belongs to F, this should imply that A complement also belongs to F. So, an algebra of subsets of a set X is a collection of subsets of X, which includes the empty set and the whole space. It is closed under intersections and it is also closed under complements. And the last time we looked at some examples of algebras and semi-algebras. So, today what we are going to look at is, the question is, given a collection C of subsets of a set X, does there exist an algebra which includes C? So, the given collection C may not be an algebra of subsets of X, it is an arbitrary collection, and we would like to know, can we find a collection of subsets of X which includes this collection and is an algebra? Of course, there is one obvious answer, namely the power set. For example, the power set of X is always an algebra, because it is a collection of all subsets of X. So, it has all the properties, namely it is closed under intersection and complements and includes the empty set in the whole space, and obviously, C is a subset of P x. So, in some sense P x is the largest algebra of subsets of X, which includes any collection C. So, we should modify our question, namely, given a collection C of subsets of a set X, does there exist an algebra which includes C and is the smallest? So, to answer that question, let us look at the following. So, let us collect together. So, let us look at the collection all F such that F is a subset of P x, it is a collection of subsets of X, and such that F is an algebra and C is contained in F. C is the collection which is given to us, which may not be a algebra. So, let us collect all those collections of subsets of F X. So, call them as F, such that, so F is a collection of subsets of X, such that F is an algebra and includes C. So, it has two properties. One, C is a subset of it, this collection C is inside the collection F, and F is an algebra. So, first of all, let us observe that P x is an element of this collection. So, let us call this collection as say I. So, this collection of all algebras which include C is a non-empty collection, because the power set of X, the collection of all subsets of X, is an algebra and includes C. So, this is non-empty. So, implies that this collection is not empty. And now, what we do? Let us define A to be equal to intersection of all this F such that F belongs to I. So, let us take all the collections in this collection, all the algebras which are members of this collection I, and take their intersections. So, keep in mind, each F is a collection of subsets and it is an algebra, and we are taking the intersection of these collections. So, the claim is that 1 C is a subset of this collection A, which is obvious because the collection I of all the algebras F has that property, C is a subset of each member. So, this property is obvious. Secondly, we claim that A is an algebra. So, to prove that A is an algebra, let us observe what we have to do. So, what is A? A is the intersection of all algebras F which are inside I. So, first we want to show empty set belongs to A. Why? Because we know empty set belongs to each F, because each F is an algebra. Similarly, X belongs to A because of the same reason, because X belongs to F and F is an algebra. And secondly, let us take a set E belonging to A, then that will imply by the very definition that E belongs to F for every F inside the collection I. But that implies, because E belongs to F and F is an algebra, that implies that E complement also belongs to F for every F belonging to I. But then that implies, it is equivalent to saying, this implies that E complement belongs to the intersection of all these F in I, and that is precisely our A. So, we have shown if E belongs to A, then E complement also belongs to A. So, the class A is closed under complements, and let us finally show that it is closed under intersections also. So, let us take two sets E and F belonging to A, then that implies that E and F both belong to each F belonging to I. But that implies that E intersection F belongs to the collection F, because F is an algebra. So, that is crucial. So, that is being used again and again. E and F belong to the collection F, which is an algebra. So, the intersection also belongs, and hence E intersection F belongs to A. So, what we are showing is this collection A, which is intersection of all the algebras which include C, is an algebra. So, we have shown the second property, namely that this collection A of intersection of all the algebras which include C is an algebra of subsets of the set X. Also, C is inside A, and by the very nature, because it is the intersection of all the algebras which include A, it should be obvious. So, obvious property, namely A is the smallest algebra of subsets of X such that C is inside A. What do we mean by that? That means that if, so this is same as saying if F is any algebra and C is inside F, that implies that this F have to include A. So, what we have shown is that given any collection of subsets of a set X, if we define A by this, A is the intersection of all the algebras including I, then this collection exists, because there is at least one algebra which includes C, namely the power set, and it is the smallest. So, what we have shown is, given any collection of subsets of a set X, there is an algebra of subsets of X which is smallest and includes A. So, we have answered this question, that given a collection C of subsets of a set X, does there exist an algebra which includes C and is smallest? Yes, the answer is yes. So, let us state this as a theorem, namely, let X be any set and let C be any class of subsets of a set X. Let f of C denote the intersection of all the algebras A which include the collection C. So, f of C is the intersection of all the algebras that include the collection C. Then what we have just now shown is that C is a subset of X. That means, f of C always includes C, and f of C is an algebra of subsets of X. So, f of C is an algebra which includes X, and it has additional property, it is the smallest with that property. That is, if A is any other algebra of subsets of X such that A includes C, then A must include f of C. So, this is not S of C, it is f of C. So, f of C is called the smallest sigma algebra of subsets of X containing C, and is called the algebra generated by the class C. So, what we have shown is that given any collection of subsets of a set X, we can always find an algebra of subsets of X which is smallest and includes it. Let us look at some examples. So, let us look at the collection X is any non-empty set. Let us look at the collection of all singleton subsets of this collection X. So, C is the collection of all singleton sets where X belongs to X. We want to know what is the algebra generated by it, and the claim is that the algebra generated by this C is nothing but all those sets E in X, say that either E or E complement is finite. So, let us prove this. How do you prove such kind of assertion? So, we have got X any set, and C is the collection of all singleton sets belonging to which are subsets of X. Okay. And then we are looking at, we claim, so this is our claim, that f of C is nothing but all sets A contained in X, say that A or A complement is finite. So, let us observe, does empty set belong to f of C? Yes, because by definition empty set is a finite set. Okay. Does X belong to f of C? So, for X to be an element of f of C, either X should be finite, which we do not know, because it is an any set, right. It may or may not be finite, but we know its complement, which is empty set, is finite and in f of C. So, by the second criteria, A or A complement. So, X may not be finite, but its complement is empty set which is finite. So, this property is true. Let us check the second property, namely, if E belongs to f of C, does this imply E complement belong to f of C? Is this true? Well, for E complement to belong to f of C, either E should be finite or E complement should be finite. So, this will be true if and only if E complement or E complement finite, which is same as E complement or E complement is E finite, which is same as saying. So, this is if and only if, this is if and only if, this is if and only if E complement belongs to f of C. So, E belonging to f of C is true if and only if E complement, because our definition of f of C is symmetric with respect to A and A complement. So, the collection f of C of all those sets for which A or A complement is finite includes empty set, the whole space, it is closed under complements. And let us show the third property, namely that if E and F belong to f of C, then that implies their intersection also belongs to f of C. Or equivalently, this is equivalent to saying that E union F belong to f of C, because we have observed that from union you can go to intersection by complements, because the class is already closed under complements. So, let us, but E and F belonging to f of C means E or E complement finite and F or F complement finite. So, various possibilities arise. So, let us take case 1, both E and F are finite. In that case, that will imply that E union F is finite, because union of finite sets is a finite set, and that will imply that E union F belongs to f of C, our collection. So, whenever E and F are finite, that's so. What is the case 2? What is the other possibility? Either E or F is not finite. So, let us, for the sake of definiteness, suppose E is not finite, but E belongs to the class f of C. So, that implies E belongs to f of C means E complement is finite. Okay. Now, E complement is finite. Let us look at now, and E is contained in E union F, but that implies that E union F complement is contained in E complement, and E complement is finite. So, that implies, so is finite. So, that implies E union F complement is finite, and hence by definition this implies E union F belongs to f of C. So, we have shown in either case, hence whenever two sets E and F belong to f of C, that implies E union F belongs to f of C. So, thus we have shown that the collection, so f of C is an algebra. So, f of C is an algebra, and it, so f of C, which was defined as all sets A contained in X such that A or A complement finite, is an algebra, and C is contained in f of C. Is it clear why C is contained in f of C? Because for every x belonging to X, the singleton X is finite. So, implying the singleton X belongs to f of C. Okay. So, implying that C is a subset of f of C. So, thus f of C is an algebra and includes f of C. Claim finally, that f of C is smallest. So, that is, let A be any algebra such that C is inside A, then that should imply. So, that is the question, that should imply that A includes f of C. So, let us show how is that true. So, to prove this, let A belong to f of c. So, two possibilities. One, A is finite. So, let us write A as x 1, x 2, some x n. That means, this is equal to union of singletons x 1, x I equal to 1 to n. And each singleton x I is an element of class C, okay, and C is inside f of C is inside A, C is given to be inside A. So, this implies that A belongs to C. Okay. A belongs to f of C. Sorry. So, this, so let me just go through again. Because A is finite, A is written as x 1, x 2, x n. So, I can write as a finite union. Each x I belongs to C. So, each x I belongs to f of C. Right. So, this implies, so here is because each x I belongs to C, which is subset of f of C. So, each one is in f of C is an algebra. So, A belongs to f of C. Okay. Oh, I am sorry, this is not what we wanted to prove. So, this is not true. This is, of course, I am proving whatever was required. So, let A be finite. So, this is okay. We want to show that A is inside the class A, but so each x I belong to C, C is contained in A, that means each x I belongs to A, and A is an algebra. So, that implies that the union, so A belongs to A. Okay. Same argument, basically using that C is inside A and A is an algebra. So, that will prove that A is if A belongs to F, then this implies that A belongs to A. So, that proves that A is a subset, A always includes f of C. So, hence what we have shown is the following, that if C is the collection of all singleton sets x belonging to x, then the algebra generated by it is nothing but all subsets A in x such that A or A complement is finite. A or A complement is finite. So, this is the algebra generated by C. So, we have computed, we have described the algebra generated by a collection C of singletons of a set x.